G'day everyone, and welcome to Lubrication Explained. Today we're going to be talking about mineral base oils and how they're manufactured. So the first question to ask is, where do mineral oils come from? And the thing that distinguishes a mineral oil from any other kind of base oil, whether that be silicon-based, synthetic, is effectively that they all begin their lives as crude oil. So crude oil is generally found by oil and gas companies all over the world who prospect across land and increasingly in the deep waters of the ocean. So if we were to look beneath the surface of the water and eventually below the earth, what we'll come up against is an oil and gas reservoir. This might look a little bit different to how you imagine it or how you've seen it in the movies. There is no lake of oil down there. It's actually within the rock. So if you picked up a piece of sandstone, that piece of sandstone has two properties which are important. One is porosity, the other one is permeability. So porosity is a measure of kind of the quantity of the void spaces within the rock. So it looks solid, but there are plenty of microscopic holes in it. And permeability is a measure of the connectedness of those pore spaces. So porosity gives you the total amount of oil or gas you could fit in the rock, and permeability kind of gives its capacity for flow. So these two properties are very important when oil and gas companies go to drill a well, because you need sufficient volume of oil and gas, but you also need it to flow. So once that oil and gas is flowed to the surface, we can then begin the refining process. If we were to look into what's in a barrel of crude oil, it's this soup of all kinds of different molecules. We've got aromatic rings, we've got naphthenes, paraffins, isoparaffins, and all sorts of different shapes and sizes of molecules. So you've got light elements, which could include gases, heavy elements like bitumen and tar. All of that is mixed together. And the process of refining is really the process of separating out those molecules into like groups that can really function as a product. So our refining process is going to begin with an atmospheric tower. Very similar to, let's say, a distillation column, which you might have used in high school chemistry. Really what that's about is trying to separate out different molecular weights. And so what we get at the end of it is a mixture of gases up the top, then you've got kerosene, then there's light gas oil and heavy gas oil. And lubricants generally come from the fraction which starts with the same weight as about diesel engine oil and goes through to some obviously heavier stuff for the higher viscosity products. Okay, so if we want to manufacture a Group 1, the first thing we do is put it through a vacuum distillation process. And that's actually very similar to atmospheric distillation. What comes out the bottom is some heavier molecules, and we want to get rid of specifically the asphalt, because that's not going to be useful to us as part of finished lubricant. The way that that's done is it's actually a propane solvent that's used to extract the lube fraction. And that's because the propane dissolves paraffinic, naphthenic, and aromatic lube fractions, and it leaves the asphalt. So the propane is then recovered through a stripping tower, and we get just the lube fractions back out of that. So what comes next? Well, you've then got the distillates, and they go into a solvent extraction process. And solvent extraction is really to get rid of some of what you might colloquially call the nasties that are present in a crude oil. So there's things like aromatics, for example, a lot of sort of sulfur compounds. So what is needed from the solvent is some kind of chemical that has really good solvency with the aromatics, but very poor solubility with the lubricant portions that you want. So as an example, saturated hydrocarbons. So these solvents are usually really polar, and they include solvents like furfural, NMP, as well as phenols. And what comes out the bottom of the solvent extraction process is actually a pretty toxic kind of chemical soup. There's not really a lot that we like about that. But fortunately, what we're left with is what we call raffinates that go into a solvent dewaxing process. Now, solvent dewaxing really fixes some of the low temperature properties of our lubricant. It helps remove some of the really long chain paraffins, which are undesirable because when you cool down those long chain paraffins, they're going to crystallize into wax. So effectively, you'll have solid particles in your lubricant, and that's obviously not desirable. So what they do is they use solvents like methyl ethyl ketones and toluene, and what these do is they actually cause the paraffins to crystallize at low-ish temperatures, and we can then remove them just with a standard filter. So once that's come out, that's wax that comes out the bottom, and then we have a dewaxed oil that goes into a hydrofinishing tower. And hydrofinishing is effectively reacting those products with hydrogen, and that removes small amounts of sulfur and some polar components, which can improve the color stability of the finished product and contributes a little bit to the demulsibility and oxidative stability performance. And at the end of that, what you have is a Group 1 base oil. So each of these four processes you can think of as contributing different physical characteristics to the lubricant. So the vacuum distillation, for example, that gives us our viscosity, flash point, and volatility. So that makes sense. We're separating out the lubricant into different molecular weights, and so that's going to give us our weight of the finished product. Now, solvent extraction, because it's removing aromatics, is going to give us our VI and our oxidation stability. Solvent dewaxing, because it's removing waxes, is going to really help our cold temperature performance. So that's pour point and the cold crank. And lastly, you've got hydrofinishing. And hydrofinishing is, going to help us with color stability. And to be honest, a little bit on the oxidation stability, but not much else. So how is the manufacturing of a Group 2 or a Group 3 different from this? Well, it's slightly different in so much as we introduce two new processes, the hydrocracker and catalytic instead of solvent dewaxing. So a hydrocracker is a little bit like hydrofinishing, except that it's a method for reducing molecular weight and saturating hydrocarbons, and it's done at a much higher pressure. So we feed hydrogen into the vessel at something up to, say, 3000 psi, and it gets reacted with the distillates in the presence of a catalyst. Now what that does is it can saturate aromatic rings, it can break open naphthenic rings, it can saturate olefins and crack paraffins, as well as remove sulfur and nitrogen. And by dialing up the pressure and the amount of hydrogen and the type of catalyst is what helps us move from a Group 2 to a Group 3. So the hydrocracker fundamentally actually changes molecules rather than just separating out into different kinds of molecules. Catalytic dewaxing is also very different to standard solvent dewaxing because the raffinates still contain some waxy molecules. So a dewaxing catalyst is here used with high pressure hydrogen, and it actually converts waxy components from straight chain paraffins into branched isoparaffins. So again, we are actually changing the physical structure of the molecules to give us more desirable performance properties. By dialing up any of these, we can move from a Group 2 to a Group 3 base oil, but we get lower yield. And that's why the Group 3s tend to be a little bit more expensive. So I hope that has kind of given you a bit of a flavor. It's a very quick primer on how mineral oils are manufactured. I'll go into some more detail about different properties of these lubricants in future videos. Thanks for listening. This has been Lubrication Explained.